In a past video series, we learned about the sampling distribution of a mean. We learned that a sampling distribution is a distribution of statistics. Now let's turn to the sampling distribution of a proportion. We can create a sampling distribution for any statistic, and so since we're interested in proportions, let's create the sampling distribution of a proportion. I'm going to begin this by doing a simulation using R. In the early 1990s, the National AIDS Behavioral Surveys interviewed a random sample of 2,673 adult heterosexuals. The purpose of the survey was to determine the proportion of the population that was putting themselves at risk for AIDS by engaging in sexual activity with more than one partner. In the sample, 170 people stated that they had more than one sexual partner in the previous year. So first we're going to calculate the sample proportion of those who say they have more than one sexual partner. This is 170, the number that said that they did have more than one partner, divided by the sample size, 2,673. Let's calculate this. This comes out to be 0.064, about 6.4%. So 6.4% of the members of this sample stated that they had had more than one partner in the previous year. We're interested in the entire population of adult heterosexuals. Our best guess right now at what proportion would say that they had more than one sexual partner in the previous year is 6.4% or 0.064. Here's what the bar graph looks like for the actual sample. You can see that most individuals said yes, they were monogamous in the past year, but here we have that 0.064 that said no. Now, to build a sampling distribution, we're going to have to repeatedly sample from the population. The population is not accessible to us. That's why we call what I'm about to do a simulation. What happens to P, the sample proportion, if we repeatedly sample 2,673 from the population? In other words, I'm going to take the same size sample as what we actually had in this study and see what would have happened if a bunch of researchers had taken the same sample size from the population and asked the same question. Let's suppose, for the purpose of this simulation, that pi, the population parameter, is 0.06. So I'm going to set pi, the population proportion, at 0.06 for this example. In our one sample, we got 0.064, so we were close to the actual value, but not right quite on it. If you are wondering how do you know that the population's value is 0.06, I do not. I'm going to run a simulation in which we use a population with a proportion of 0.06 who would say that no, they were not monogamous in the past year. I am going to take 10,000 samples of size 2,673. Remember, what's of interest here is the sample size, 2,673. To create a sampling distribution, we would take an infinite number of samples, but the problem is I don't have enough time to take an infinite number of samples, so I'm going to take a large number, namely 10,000. Here we go. I'm now going to look at the histogram of the proportions for each sample. So I now have 10,000 samples, each of them size 2,673, and I've calculated P, the proportion who said they were not monogamous in each sample, and I'm going to now look at a histogram of those p-values. Look at that. Just like what happened with the mean. It doesn't matter that our original population might not have anything that looks at all like a normal distribution. Look at that one sample that we took. If the population looks like this, that's not going to be a normal distribution. And in fact, the population will have no's and yeses with a larger number of yeses than no's. I can even superimpose a normal distribution on this. This is something that you as a researcher will not have to do. We're just learning theory now, and we're learning theory about the sampling distribution of P, just like we learned theory about the sampling distribution of Y bar, the sample mean. Let's take 10,000 samples again, but this time, instead of taking a sample size of 2,673, let's take samples of size 500. Still a large sample, but a lot smaller than 2,673. Again, I'm going to calculate P, the proportion, for each sample. There's the histogram. Once again, we got a normal distribution. Once again, we can superimpose a true normal distribution to show that this histogram is very close to normal. So what does that tell me? Looking at both of these histograms that I created, I can see three things. First, the central limit theorem applies to proportions just like it applies to the mean. Look at a sample of size 2,673. When we took 10,000 samples, those 10,000 sample proportions were normally distributed. When we took samples of size 500, those 10,000 sample proportions were normally distributed. So we see that the central limit theorem works. What about the law of large numbers? Well, in this particular picture, in which we had samples of size 500, the range from the lower end of the distribution to the upper end of the distribution is about 0.02 to 0.10. But what about when we took samples of size 2,673? It's about, say 0.045 to about 0.075. It's a much smaller range. So what happened when we took larger samples? The sampling distribution has less variability. So the law of large numbers works as well. Finally, we said that in the population, the true proportion was 0.06. What looks like the mean of this distribution? 0.06 looks right in the middle. What about this one? 0.06 looks right in the middle. So even though each of our samples could yield a value that is different than 0.06 on average, the mean of our proportions equals the population proportion. Thus, P is unbiased. So let's summarize what we've been discussing. Let's talk about the sampling distribution of P. We know that it is normally distributed, so the central limit theorem applies. The variability of P decreases with larger sample size, so the law of large numbers applies. The statistic P is unbiased. Here are some properties of the sampling distribution of P. Because it's an unbiased statistic, the mean of P is equal to the proportion that we're trying to estimate in the population. The standard deviation of P is the population proportion times 1 minus the population proportion divided by the sample size, and then we take the square root. This shows us that the law of large numbers will work because the sample size is in the denominator. The bigger we make n, the smaller the standard deviation of P. Now the problem here is in order to calculate this, we would have to know pi, the population proportion, and we're not going to know that. So we're going to estimate using the standard error of P, and notice the only thing that I've done is replace pi the population proportion, with P as our best estimate of the population proportion. Those are the properties of the sampling distribution of P. With these properties in hand, we can move forward and learn how to make inferences about the population proportion.